All right, let's look at the last example problem for this week, which is example 13.2. So this is the example from your textbook. So I'm going to share my screen. Okay, again, this slide is available on the Blackboard, so you can download it and go over the same slide with me. All right. So here's the problem. A force of 150 pounds is applied to the edge of the member as shown in this figure. Neglect the weight of the member and determine the state of stress at points B and C. So here we have a force, and these two lines are the center line along each dimension. Okay, so the entire height of this kind of a column is 10 inches and 4 inches in this way. This 150-pound force is applied right here. Okay, if that with that force, what about the stresses at B and at C? Okay, that's the question. All right, so in chapter 11, when we talk about the beam bending, we learn how we can calculate the bending stress. So the bending stress equation looks something like this. Sigma is equal to negative my over I. So m is the bending moment, y is the distance from the neutral axis of the section in the vertical direction, and I was the moment of inertia. Okay, and we also learned in the first chapter in this class was the stress, right? So we talked about the normal stress due to the actual force, and the equation was sigma is equal to P over A. So in this problem, because this is, if the force 150 pounds is going to be applied exactly at the centroid of the section, then we will have the exact and uniform distributed stresses all over the area, which looks something like this. So we have the normal stress due to 150 pounds. If the force is applied at the centroid here, then the stress is equal to 150 pounds divided by the cross-sectional area, which is 10 inches times 4 inches. And it is going to be uniform. But now the force is not exactly here. It is applied on still on this vertical line, but there is an offset from this horizontal line. Okay, let's say this is a vertical direction, this is horizontal direction. Now this applied force is moved from the center line vertically down at this edge. So this 5 inches is going to be the offset, and that offset will create a moment. How much? 150 pounds times this 5-inch offset will become a moment. So I can draw this structural system here again. Okay. So now this is the vertical line that I'm talking about, and here we have a horizontal line, and the force is applied at this edge, right? So from this central line here, this offset is going to be 5 inches. So the corresponding moment due to this offset is going to be 150 pounds of force times 5 inch the moment arm. So it is going to be 750 pound inch. So that is going to be the moment here. Now, this is the typical equation. So because we talk about the beam bending, then beam is the horizontal member usually due to the transverse loading on top. So because of this offset, we can say the moment is applied this way. But we can also say when you just change the orientation, okay, like this, then I can also say that it's kind of a beam and apply at the moment is something like this. And we always talk about this, right? And the corresponding stress due to this moment was this, let's say this is the neutral axis, and we will have the compression on top and the tension at the bottom. So this is going to be the tensile stresses, and it is going to be the compressive stresses. Remember that? and the y is the distance in this way, the vertical direction. So that was y here. And the moment of inertia is coming from this cross section. So that's what I'm talking about. And because in this case, the C is this bottom edge along this bottom, right? And point B is here, so that is on top. So we can easily say that only due to this bending moment, it is gonna be the corresponding stresses due to the moment is gonna be the stress value corresponding to the moment is going to be either the top here and the bottom, which are going to be the maximum value. And we had another equation for maximum stress. Sigma max was equal to m times c over I, and the c is the maximum y value. So when you maximize y with a given moment, we were able to get the maximum sigma value, right? So we can also use this equation. So I'm going to use this equation. So what is this sigma? So basically, how can we find out the stress at B and C? Well, we're going to combine these two together because the stress at B is going to be not only just the normal stress due to the actual force, but also because of this offset, we have a bending stresses as well. So we're going to combine these two stresses together. So let's calculate the normal stress sigma using this equation first. So I said P is 150 pounds and A is 10 times 4. So when you do the calculation, 150 divided by 40 inch square, I got 3.75 in PSI. Okay, so this is uniformly distributed stresses all over the area due to the actual force. And as you can see, this is in compression, right? So this is in compressive stress. Now, what about the bending stress? We're going to use this equation for B and C. It will be the same. So when we calculate the bending normal stress due to the bending, I'm going to change the color. So sigma max is equal to m, the bending moment, which is this 750 pound-inch. C, what is C? C is going to be the distance from here, the neutral axis, to either top or the bottom, the same value, which is 5 inches. So 5 inches divided by the moment of inertia. So we have to calculate the moment of inertia, BH cubed over 12, which is 1 over 12. B is going to be 4. H is 10 cubic. So when I do the calculation, sigma max at either the top or the bottom. In this case, the top is going to be the tensile stress, and the bottom is going to be the compressive stress. Anyway, the magnitude is going to be 11.25 in PSI. So when I draw a stress distribution due to the moment, so this bending moment here, I'm going to draw it here. So we will get the maximum compressive stresses here. And then in the middle, it's going to be 0. So it is going to be decreased from the maximum value to 0. And then it will have a maximum positive, the tensile stress, the other end here. So okay, here we have a stress diagram. Okay, so this is going to be in compressive stress, going down to 0 in the middle, and then it changed the direction to the tensile stress. So this is going to be 11.25 in tension. This is 11.25 in compression. And we're going to combine these two together. So what is going to be the sigma in at point B? So sigma at B will be equal to, one is in compression, the other one is tension. Usually we use a positive sign for tension and negative sign for compression. So it's sigma B is going to be now 11.25 with positive sign, and then 3.75 with the negative sign. So I'm going to subtract that, which is going to be 7.5. Okay, in the unit is going to be psi. And I got positive, which means this is going to be in tension, which makes sense because we're going to apply the one normal force in the downside here. So the top portion is going to be in tension, right? Now, what about sigma at C? Sigma at C, we have 11.25 with compression. Compression is negative. So in this case, both stresses are going to be negative. So we will maximize the negative stress. So it's going to be negative 11.25 minus 3.75. So it is going to be negative 15 in PSI, and that negative sign means compressive stress. So negative 15. All right, so those are going to be the answer. Determine the state of stress at points B and C. At point B, we have a tensile stress, and the magnitude is going to be 7.5 psi. At point C, it is going to be compressive stress, and we maximize it due to not only just act normal force, but also due to the direction of the moment. This half is going to be in compression, the other half is going to be tension. So the maximum, the corresponding stress at C is going to be negative 15 psi. All right, so those are the answer for this question. And this is the end of video number 4. And this is the last video for this week. So have a great weekend and see you next week. Next week, by the way, I'm going to post the review session, again, another video clip to prepare your party number 2, okay? So I'm going to prepare the video and then post it on the Blackboard and let you know via email. I'm gonna assign the entertainment package on the mastering engineering to cover chapter 12 and 13. Okay, so chapter 13 is pretty small chapter. So I'm gonna combine chapter 12 and 13, and I'm gonna assign the entertainment package. Since next Friday is the Good Friday, and next week we will have the second midterm exam. I'm going to give you 2 weeks to work on this entertainment package. So the due for this entertainment package, I think is number 7, will be Friday, April 17th. So you have plenty of time, even after the midterm, to complete this entertainment package. So enjoy your entertainment package as much as you can, and then have a great and blessed weekend and stay safe. Bye.